It's a great pleasure to see many of the faces I've seen on Monday, and I think there are a few new people that came. So I'll just very briefly say that it's a great pleasure to have Professor Barish give the second Green Family Lecture. So the Green Family Lecture Series is an event that we have at IPAM, the Institute for Pure and Applied Mathematics on the UCLA campus. IPAM is an NSF-funded institute, and its mission is to bring together mathematics and other disciplines. So this week we have a workshop on gravitational wave, on computational challenges in gravitational wave astronomy, where we're trying to bring together people from physics, from computation, from mathematics. And this is our mission, to bring mathematics with other disciplines. The Green Family Lectures is an endowed series. It was endowed by Mark and his family. Mark Green is a founding director of IPAM, and I think every time I say this, he deserves an even bigger round of applause for both for giving us a good endowment to be able to run these lectures, and also for the whole idea of starting these things. The lectures have brought very eminent scientists to UCLA and IPAM over the years. Again, thank you so much for coming. Just like on Monday, there will be a reception at IPAM following this lecture. So let me now introduce Marco, who will say a few words about the speaker.
Thank you. Hello, thank you for coming this evening. We'll have another amazing lecture by Barry. It's a pleasure to have Professor Barry Barish here to give another lecture on gravitational waves. He's a colleague of mine in the LIGO Scientific Collaboration. He's going to tell you all about LIGO and the detection of gravitational waves. Barry has a career that spans many decades in physics. As many of my colleagues, he started with particle physics, and then he was drawn to the dark side of astrophysics, and I really mean it. Black holes are really dark. And I won't make a list of all the recognitions of Barry because it will take too much time. Let me just say that, of course, 2 years ago, Barry with Ray Weiss from MIT and Keith Thorne, also from Caltech, received the Nobel Prize in Physics 2017 for the discovery, the direct detection of gravitational waves by LIGO. And Barry, since the 90s, had a fundamental role in the LIGO project. He had the vision to, put together the LIGO Scientific Collaboration, really create the structure that allows us nowadays to be able to do the science of gravitational waves, run the detectors, and do these amazing discoveries. And that's one of the many and great contributions of Barry. I won't take much more time because I know that you are all there waiting to hear from Barry. So gravitational waves and future new science. Thank you very much.
Thank you. Okay, this lecture is meant to be almost independent of the last one. So those of you that are here the first time, the reason you don't understand it isn't because you weren't here last time. In fact, as hard as I try, I expect this is less accessible because last time I talked a lot about history. We all know history is complicated. There's revisionist history and so forth, but history is still easier to talk about than the future. In fact, those of us that are doing the science don't really know the future, so we're speculating. But I've chosen to talk about the future after I do some more talk about gravitational waves and detecting them first, because we're really just beginning this adventure. And it's a brand new science, and I want to kind of paint at least the way we see how it should evolve in the coming years and what some of the options are. The real way that it'll evolve will undoubtedly be different than I present, so I'll do my best to tell you what we're looking at. So our best guide at what we'll see, and I'm going to concentrate more on the astrophysics than the general relativity. One thing that's rather clear is that we now have the best tool to test Einstein's theory of general relativity, and hopefully out of that, we'll learn whether his theory is the right theory or the variance that exists in nature. So far, we've done tests with the data we have and that I will show and that I showed last time, and we see no hint of any deviations from Einstein's theory. However, we know that as good as that theory is, and it's used for long distances and high velocities, relativistic astrophysics, physics is populated by two very successful theories. The theories that are used at very short distances, quantum theories, explain almost anything that we do when we crash particles together at a big accelerator like the CERN collider. And it's an embarrassment for physics, I think, and I think most of us think, that we have two fantastically successful theories of physics, but never the twain shall meet. One works at long distances, one works at short distances. Maybe that we'll find ways to bring that together experimentally by looking, for example, beyond just detecting them, at some places in nature where both theories have to apply. One place is black holes, for example, which I talked about. Now, we're just detecting black holes, not really studying them yet, but in the future, studying black holes might be a place where we obviously have Einstein's theory of relativity applying itself, but we have to also conserve all the quantum numbers and all the things that have to do with quantum physics. So it might be in the future that we, as physicists and scientists, will learn how to bring these together. So I'm starting the talk with a speculation, but what I'm going to do is start from a more basic idea of what we can measure in the coming years incrementally and where this might lead. And maybe at the end, we can reach the large questions like the one I just posed. So far, and in the last lecture, I really talked about astrophysics sources that we knew in principle exist from measurements that are done in regular astronomy and astrophysics, and that is that there are systems around neutron stars, for example, in our galaxy that have been seen to be in pairs and could eventually, by Einstein's equations, merge. And I showed that in the last lecture. And that's an obvious first source and was a big target of ours, and I'll show a little bit more on that now. But there are several other sources, and I'm going to go through that we know enough about from astrophysics that we can expect in the future, and I'll try to give you a sense whether I'm talking about short-term or long-term future, to start learning about in terms of the gravitational effects. In the end, it's the combination of studying astrophysical effects with all the tools we have, with electromagnetic radiation, maybe with neutrinos, and with gravitational waves. That's what this little conference is about here today. They give us the combined tools to really make the next steps in astrophysics. Anyway, this little hand drawing we made 25 years ago or so, which was our hand rendering of what we actually discovered as the first gravitational wave sources. And that is that what you expect is that in nature, there's some compact objects, which we knew about from astrophysics, that are paired together, holding around each other, just like the moon around the Earth around the sun. It's not surprising that compact objects like neutron stars would do the same thing, or black holes, for example. They're also spinning, each of them. So far, in the data that I talked about last time and we'll talk about today, we have very little ability, because the data is not good enough to say anything much about these spins. And as they go around each other, they pull on each other, and by Einstein's equations, they radiate away gravitational radiation, which is seen here. And this part of the problem we know a lot about, and we calculate it using Einstein's equations. And that's what we did to detect gravitational waves. There's a part of the problem that requires a lot of theoretical work, and we only learned how to do not long ago, and that is to actually determine what these shapes are in Einstein's equations for different masses and different combinations using what's called numerical relativity. And that's relativity done on a computer. It turns out that that's a very difficult problem, and I'll show you why we do that in a minute. Or I'll mention why we do that. There are three known sources of binary systems that are compact that should give enough gravitational radiation so we should be able to detect them. The first one that we detected, this is in the order that we expected to be able to detect them because we knew from our own galaxy how many neutron stars there were, and there were some pairs that had been seen. And we could estimate from that, crudely, how many there probably are in our galaxy, just by what we'd seen fractionally, and assuming that other galaxies are similar to our own, probably not a terrible assumption, but maybe not a perfect one, we could estimate how many gravitational wave neutron star mergers there would be, where when it merges in the very final steps that we could detect them, and how far out we'd have to look. And that determined the sensitivity in the design of the instruments that we built. After they merge and come together, this is the very interesting part that we know very little about, because that's the part where gravity is the strongest. They're merging together completely. We can't calculate, we can calculate the energy here, but we can't really calculate the detailed shapes here. And this is an area that in the future we'll study quantitatively in great detail to understand all the details of these mergers, which are different for black holes, which are objects that no other information goes out, and for other objects like neutron stars. Let me mention again, the difference between black holes and neutron stars are that neutron stars are nuclear matter but very dense. They come about by the collapse of a star when it burns up all its fuel and has what we call a supernova. It's very tiny afterwards. And these mergers could be black holes and neutron stars, black holes, but it could also be a black hole and a neutron star. We look for those, but we don't yet know very well how to calculate what we're looking for, and it limits our ability to look for those. So the fact that we haven't seen them yet is a physics problem that we still have to solve. The problem is when the masses of these two objects are more like the moon and the earth or something, one is much bigger than the other, it's very difficult to do the calculations. So since we compare calculations with anything we see right now, I'll mention other ways of doing it as we go along, then we have to see things in that way. In fact, the technique we use is called match templates. So what we do is take our understanding of these two objects going around each other and using Einstein's equations, and we calculate as many combinations of them as we can, as would fall into our sensitivity of our apparatus. That turns out to be hundreds of thousands. So to cover all the possible combinations of this one going around that one and their masses and so forth is hundreds of thousands of templates that we calculate that look a little bit like this. I'll show you the ones that we've seen look different from each other, so you'll get a sense that you need a lot of them. And every piece of data, as we observe, we compare with these 200,000 templates. If we see anything that matches, then we pull that out and analyze it. So that's what's called matched templates. And that basically is the technique we use, and you can see kind of in this picture here, if the two objects are lighter, by the time they get into our frequency ability, we can see down, we're in the audio band, so as long as they're going around each other slowly, we can't see them. But if they get up to more than 10 times a second that they're going around, then they're in the audio band, just like the ears couldn't hear if it was too low in frequency, and we start seeing them. If they're light, like these, then we see many, many cycles, and you'll see that in the data that I show you. And if they're very heavy, like the very first one that we saw, we just see a few cycles because it barely got into our frequency range. So even seeing this little picture here, you can see there's many possibilities, and we have to compare all of those possibilities with every piece of data we have, and that's a big data analysis problem. So this is what it looks like, that what we expect it to look like without a freehand drawing, but more of a real drawing of what you get if you calculate. We call it the in spiral, when they're just slowly coming into each other. And of course, here is again when they've reached something like 10 hertz or so I'm showing. They're back here, and when I talk about what we can do in space, we could see these much earlier in space. So we see them coming in, and basically they're going, this is basically the cycle of them going around each other and how much energy is being released as they come closer and closer together. There's more energy, these get taller. This is measuring the strain or the amount of energy. And the frequency gets higher, that's why these get narrower. And eventually they come together. And then it all has to settle down. That's what we call the ring down here. And so this is all that we look for. Right now, this is really where the main information is. In the future, there's this, and possibly effects later, for example, in the neutron star case. So we have a lot to do to understand things later, but what we've been able to do is to understand and compare this first part of it, what's called the merger, and the amount of energy, at least, that goes into the the in spiral, and then the amount of energy that goes into the merger, and the characteristic frequency of the ring down itself. So that's kind of what we've done. Okay, the effect is incredibly small. We can take these two objects and their masses, and we can calculate what the effect is using Einstein's equation. And using Einstein's equation for the kind of masses and things that we're talking about, tens of solar masses and some distance that's reasonable out in the universe, that's like we've detected, something like a tenth of the way out in the universe maximum. The strength of the effect, which is given, and it's called the strain in Einstein's equations, is given by this little h, and it's a dimensionless number, and it's tremendously small. It's 10 to the minus 21. And that is the experimental number that we measure. We measure the strain. It has the effect of distorting space and time. And I show that pictorial here in terms of space think about this as a ring of free masses. They're free to be moved. And if a gravitational wave came through, like came through the board, it stretches it in one direction and squashes it in the other direction. And then a half a wavelength later, it goes the other way. It becomes longer in this direction and shorter in the upward dimension. And this delta L is what we measure. And it's proportional to the strain. So the strain that we measure is proportional to a change of length over length. This delta L over this L. And therefore, if we make L very, very large, then we can have a better chance to see a little h. And that's what we do. And that's why we make the detectors as large as we do, something like kilometers in length. Okay, so this is what we built. I'm going to go through some of the experimental subtleties in a lecture to the conference tomorrow. I don't have time to do that today because I chose to talk more about the future than the technologies today. So I'll just give you a little bit of an overview. We have two detectors. The reason we have two detectors is a combination of several practical reasons. The first is gravitational waves had never been seen. And if we want to convince ourselves that we really see gravitational waves, we better make sure that we're not just seeing some funny thing. And actually, therefore, having two detectors separated by, in this case, 3,000 kilometers, 2/3 of the way across the US. And the signals we require, if they're from gravitational waves, would arrive at these two at the same time if the gravitational wave was coming like this. And if it's going this way, the difference between when it's seen here and here would be the speed of light to go that far. That's 10 milliseconds, or this way 10 milliseconds. So we require that these signals come within 10 milliseconds of each other in these two distant experiments. Most of the backgrounds that we expect on the Earth's surface travel more like the speed of sound than the speed of light. So backgrounds from something on the Earth, which we have to worry about, are almost all eliminated by having two distant targets. By seeing when it happens here compared to when it happens here, you could tell by what I said already, it gives us information on the direction. So we just decided to build two. They're 10 milliseconds apart. That also says we have to tell the time of a signal accurately to something less than 10 milliseconds, which we do. The experiment itself was proposed by a group from Caltech and MIT, a forced marriage. We were both at Caltech. We were developing the ideas how to build a detector, which overlapped a lot. Work done by a group at MIT, and the NSF didn't want to fund two separate groups having such an overlapping problem, so they basically forced what seems like an unusual marriage between Caltech and MIT, but it's been a very successful collaboration. We then proposed to build build two things, like I'll show you, one near the Edwards Air Force Base in California, one near in southern Maine, not so far from MIT. We didn't really propose that. We couldn't do that. The government doesn't let us do that. Instead, in the proposal, we basically said to have some realism that we would show how it would work on two sample sites. So they were suggested sites that we had studied. It went into the political system, and you can see they rotated it by 45 degrees. And we ended up with, since this whole thing took over 20 years, we ended up with very supportive senators from these two states, and that helped us a lot. And the decision, as you can imagine, was quite political because this costs a fair amount of money. So those are the two. This is what they look like, and as I say in the meeting tomorrow, I'll describe these in a little bit of detail. I'm not going to do it today. They're 4 kilometers long, and they're in totally different topology, and they work exactly like each other if we do the same things to each other. So basically, at times, they've worked differently from each other, but it's because of technical differences. We installed a new laser in one before we did it in the other, and so forth. But they basically are identical, even though they look very different in this kind of geography. Okay, that's your experimental part. This is what we saw in the early morning of September 14th, 2015. This is the same strain. It's in units of 10 to the minus 21. So we expected a signal of something like that, and that's the maximum of this signal we saw. Well, it's not surprising because we designed around that. So finally, when we had a source that was big enough to be like that, then we could see it. And that meant the source had to be close enough to the Earth for us to detect it. It turns out that's not so close. They were black holes in this case, and it was 1.3 billion light years away where this event occurred. It looks a little bit like the pictures that I showed you. These are wiggly because there's noise, but it's basically going up and down, getting narrower and bigger, and coming together. And this is detected in Louisiana, and 7 milliseconds later, it's detected here, and they look very much alike except for the color. And if you actually draw through them, and I don't know if you can see the difference between the previous one and this one, has lines drawn through it in white. It's not easy to see if you don't know they're there because those lines fit so well. And they're the lines calculated from Einstein's equations. So this data, and something, since I've done physics for many years, is really pretty unique. There's no data analysis done. We saw this, except for one point. We saw these two graphs here immediately. They're not massaged and gone through big computer programs. They're basically what's detected and recorded with only a bandpass, that is frequencies that are way outside of our frequency range, high frequencies and low frequencies, which don't apply, we remove. But everything in the frequency band, audio band is kept. So basically that's the only thing done, and the data appears like this. One way to look at the data and how well it really fits, and something you do as an experimentalist when you have data, is to compare the data with the experiment. And I've pulled it apart here so you can see it. So the top one is the data. Those are those two graphs of data that was just what we saw from the instrument. These are the calculations from using numerical relativity and relativity itself of the waveforms from Einstein's equations. And the way we usually see how well it fits, other than just calculating it by statistics, is to subtract one from the other and see if there's any residual effects that you see. That's what's shown here. And you see just this noise going up and down with no patterns gives us the feeling immediately, this is just what you do at the beginning before you do many other checks, the sense that there's nothing, that the fit works and there's no other effects. There's no some waviness or some other effect that we haven't seen. And lastly, this is a time frequency plot, time going this way, 0.2 of a second. Frequency this way, it's going up in frequency. So what you expect is something that looks like these curves here from the two sites. That's usually referred to, you see it goes up to 400 or 500 hertz, starts at something like 20 or 30 when you can see it. And that's the so-called chirp signal that we expected. That is, it increases in frequency and in amplitude together. It goes whoop, and that's the so-called chirp signal. So that's what we see. And the last thing is the picture of this is here, coming together closer, merging, and finally ringing down. And I just wanted to point out again that these are going at relativistic velocities. This is 0.3 the speed of light when it enters our detector, and up to 0.6 or so by the time they crash together, and that they're very close together. This is in units that you don't know, but this is about 100 miles when they at the start when they come together, and of course they go to 0. So basically, I want to emphasize by just showing them on a map that the distance apart isn't very different than what I drew on this map was the distance between, say, Westwood and Irvine, two UC campuses. And the two objects that are shown are about the size of the black holes at the time they're that far apart. They're going at about half the speed of light. And each of them is about 30 times the mass of our sun, which is 10 million times the mass of the Earth, all compacted into that much space. So it's pretty unbelievable what we're seeing at that point. Okay, so we did that, and then we have improved the apparatus some and taken data over a period of a couple of years since that discovery. And during that time, we've now seen a total of 10 reported a total of 10 reported black hole mergers. I show this to say that there's 10 because people always ask me, but to also show you how different they look from each other. Some of them have many, many cycles, and they're pretty small. They're further away. They're also smaller if they have many, many cycles. The very first one is shown here. And basically, it's the combination now of looking at all of those that we're trying to use to understand questions like what is the origin of these black holes, and what are the actual dynamics as they're coming together of the black holes, and the tests, as I said, of Einstein's equations and so forth. Near the end of after we had detected 9 of these, I think, near the end of the last run, we saw an event that didn't take a few tenths of a second, but took 2 minutes in the apparatus, and you're seeing it here. The apparatus itself, this is the time frequency, so this is time, this is frequency. The computer can see it right away, but you see a line along here, and you'll hear it in the very end, maybe. You might have heard the little chirp sound at the end. This we saw not so long ago on the 17th of August in 2017. Just before we were turning off the apparatus for a year or so, we're still off, to improve it. This immediately was obviously a different kind of event than anything we had seen before. Those all took, at most, a few seconds. This took tens of a couple minutes altogether. I've shown the last 30 seconds in this plot here. And so we knew immediately that it was from a different source, and it was a pair of neutron stars. So this was our first observation of neutron stars. Now let me go back again and tell you the difference between black holes and neutron stars. Black holes, these black holes, we believe, come from the collapse of a star, but the star has to, that is, the star is burning by the fusion process. That's pushing it out. Gravity's pulling it in. And as the star burns, it burns up the light elements first and then moves to heavier and heavier elements. Pretty soon you get to main elements being something like iron, and the fusion process ends by that point. And so there's gravity, but there's no more fusion, and the star collapses, and that's why stars have a finite lifetime. When they collapse, all the matter comes together into a small area by the force of gravity. And if the gravity is strong enough and the star is big enough, that can become a black hole. That is, the gravity is so strong that no light can get out. That won't be true when our own star, the sun, burns out. We think a star has to be at least 3 times the mass of our sun to make a black hole. So those are the ones we saw. Those were from heavy stars. We're still puzzling about where the origins were and so forth, and that's part of our studies. This one, we believe, is lighter because it went to high frequencies, and is most likely, and from all the studies we did, a neutron-star merger, which we saw. So it turns out that that merger happened, we can see here, and it's shown as a line. And it turns out that within 2 seconds of that, the black holes, by the way, emit nothing electromagnetically. So people have looked at our black hole events. They didn't see anything in any sort of telescopes. But if we make a lighter object like neutron stars, then they can emit light or other frequencies of radiation. And that's what we expect to happen when a neutron star comes together. And believe it or not, what happened here is it came together, and it turned out that a satellite experiment was looking at the same region of the sky and saw this bump, which they interpreted as a signal of gamma rays, a burst of gamma rays, at 2 seconds after our merger. You expect there to be some time difference because the merger is just the coming together, and the gamma ray signal is from the nuclear physics, so it comes together after they've merged, but it's 2 seconds. By the way, that's 2 seconds out of, because I'm going to forget to say it otherwise, 2 seconds out of about 100 million light years, which is how far away we think this object was. And 2 seconds out of 100 million light years isn't very much, and it agrees, at least experimentally, quite well with the fact that Einstein believes in his equations and his theory that light and gravitational waves will have the same speed, the speed of light, we call it, because this light was known first. So we know now experimentally that they're pretty close. This is the globe. This little circle here is the region that this satellite knew that the gravitational wave came. And by this time, we had a third interferometer in Italy, not ours, run by a European group, Italian, French, Dutch, and so forth, and that began to work. And with them, we determined that it came from this part of the sky. This picture has always pleased me because I went through years of astronomers telling me that we couldn't work together because we couldn't see accurately enough where something comes from, because they don't like to have to move their telescopes around too much. They have to know where to look. And it turns out the very first thing that's observed, of course, we saw it much more accurately than they did. So that was personally very pleasing. Anyway, so this was what was seen. That gave enough credibility that something real had been seen in that place of the sky. There was probably a gamma ray burst that maybe came from neutron star merger, whatever is known immediately or thought to be immediately, to alert every astronomical instrument of any note in the world. I think there's something like 4,000. And I think something like, in the end, 2,000 different astronomical instruments, the largest kind of campaign ever in astronomy, pointed to the place in the sky where we saw this event. That included, of course, us in gravitational waves. It included visible light, infrared light, radio waves, anything, gamma rays, X-rays, and even neutrinos, although the signal was not seen in neutrinos. That then was used to analyze all that happened when these two neutron stars came together. And there's a very nice theory developed by a physicist, I think he maybe was here at this meeting, but I didn't talk to him, from Columbia, that described what should happen when two neutron stars come together, a so-called kilonova, Brian Metzger. And this picture of all that was seen, this is the measurements, I'm not going to go through them, in gravitational waves, X-rays, gamma rays, ultraviolet, optical, infrared, radio, everything you can imagine, and all those signals traced and then analyzed for everything from the evolution to the colors to the amount of energy and so forth. And that's the picture that we have. I, of course, in this lecture can't go through all that, although Brian had a very nice theory, but I'll point out one outcome that's not definitive, but the way science develops. So we've had a puzzle in physics that goes back longer than I've been a physicist, which is the lack of ability to explain how in the Earth, when it was formed, we got heavy elements like gold, platinum, and so forth into the Earth. Where do they come from? We know that the universe is mostly made out of hydrogen and helium. We know that we make heavier elements in this fusion process in the stars. So you can imagine how you can get elements up to maybe iron from the fusion process, but how do we get yet heavier elements? We have a periodic table that we all learned in school. The periodic table has developed, at least the last parts of it, usually always in the laboratory, not in nature, but in the laboratory by taking a heavy element, bombarding it with a lot of neutrons, and then you make yet a heavier element. Anyway, for the explanation that we had as physicists, people hypothesized that there was a process called the R process, but a process that happened in the collapse of a star that enhanced the making of heavy elements. It's because physicists have to try to explain everything, even if we don't know what it is. So it was explained in that way. Well, in fact, now we've seen that we have something that happens in nature, which is a little bit like what's happening in the labs. Neutron stars, neutrons coming together and hitting heavy elements when these two objects come together. And at least some people have, this you can't be definitive based on one observation, but looking at this one observation, it's probably the best explanation we have as of today, if we see enough neutron stars and so forth to make it stand up in the future, that the heavy elements were probably dominantly made in the past by mergers like we just detected in the neutron star case. And so if nothing else, if you're wearing a gold or platinum ring or jewelry or something, you probably owe it to the science that we've just done. Anyway, now I'm going to go to the future and hypothesize kind of where we're going to go, what we might detect, and what we'll do to improve the instruments to move into the future as we go. We've actually run LIGO, our instrument's called LIGO, Laser Interferometer Gravitational-wave Observatory is the acronym, twice. The first time is when we discovered gravitational waves. We've run it in the past, but it was before we improved it. so that it would make detections, which I'll describe tomorrow in the technical meeting. The first one, we discovered gravitational waves from black holes. The second one, second run is where we just saw the more examples of the black hole mergers, but saw the first case of the neutron-star merger. We've been off for a year or so. These off periods are crucial to us. They're basically when we then lick our wounds from everything that didn't work or didn't work as well as we would like. Also, everything we learn that we can make work better, and everything we haven't put in yet that are the best ideas we have to make a more sensitive detector. And so we've been working for a year or more to prepare for a new run, which will start, we think, this April, if we're ready. And we'll run for another year and hopefully see more of some of the things I'll talk about as I go along. And each time, we're improving how far out we look. So this is in units that astronomers use, megaparsecs, but we saw 60 to 80 megaparsecs out for black holes the first time, neutron stars, 60 to 100 the second time. We think we'll be out to 120. Those numbers are incrementally bigger by a factor of 2 or 50%. The gain is actually as the cube of those numbers. If we can see further out in the universe, then the volume, or the number of stars, or the number of galaxies, or the number of black holes you see, goes as the volume, so it goes as the cube. So when we go from 60 to 120, say, which is a factor of 2 improvement, it actually gives us a factor of 8 more volume of the universe, and that much gain in our ability to make detections. So those are the kind of improvements that we're making technically as we move to the future with the present detectors. Second thing that we're doing is to instrument ourselves so that we'll be able to point accurately in the sky at anything we see by having good enough coverage in the Earth. And presently, we have the instruments that I told you about, one in Washington, one in Louisiana, one in Italy, and there will be 2 more in the coming decade, one that we're building in India, and one that the Japanese are building in Japan. With all of those together, we'll have the ability to tell quite accurately where something comes from everywhere in the world. This is our situation now. And on this neutron star that I showed, we were lucky. It happened to be that it came from somewhere where these errors are small. The size of these bananas or errors are how well you can tell depending on where it is with the present instrument. And by about 2025, when we have all 5 interferometers, then we can see quite accurately everywhere in the world. So I'm just trying to give you a sense that this is going to be evolving instruments that'll be able to do the science that we haven't done yet, whatever it is, whether it's the science that I'm going to talk about or not. And technically, we know how to keep improving it. So the message here is that as experimentalists, as hard as we've worked for 20 years or so, we're not limited by nature, we're limited by ourselves. That's a very important statement. We're limited by our ability to implement the kind of technologies that can make a quieter system where we can see smaller signals, but we don't have some fundamental thing that's limiting us there. So I give a long list of all the things that we can do to fix it, but just to give you a sense, we can make these mirrors they're heavier that we use on the instrument. We can change the materials of the mirror and make a better mirror. We're working on that. A big change, if we knew how to do it, is to move from room temperature to a cold device, which has less molecules moving around in the mirrors and so forth. We reduce what's called thermal noise. We also can improve the coatings that we have on the mirrors themselves. We can improve the power of the laser by a large amount. We're not limited by something in lasers themselves. We just have to develop a laser that's powerful enough to do this. And that'll give us the ability to, just in crude terms, to improve the kind of events we've already seen at the point where the signal to noise in those events will be much bigger. So the signal's much bigger compared to the noise. That'll allow us to, for example, in the very first science that I talked about in the case of black holes to understand the spins, for example, of the initial state. Seeing that takes better data than we have at present. We also will be able to see further out, which means we start to be able to do something which in my belief is really the long-term future, and that is to do cosmology with gravitational waves. And we'll have lots and lots of events as we improve things. So these lines on here are different technical improvements that we can make. And that's in LIGO itself. We're also looking at how to make a better detector than just improving the detectors that we made that made the first detections. This is the work that's been done in Europe to make a detector. They want to build a detector that instead of looking like an L is a triangle. Excuse me. It's deep underground. It's 10 kilometers on an arm, and it's a triangle, as you can see. So that's their idea. Physicists don't all have the same idea. We're actually talking about making another instrument on the Earth's surface, like we already know how to do, but making it 10 times longer. Then we have to deal with the curvature of the Earth and finding a site to do that and so forth, but it has less new issues than going underground. So these kind of debates are going on in the community now, but it gives you the idea that first, the present detector, we're not fundamentally limited, because I'm going to show you the physics next. We're not fundamentally limited, and in the future, it's almost inevitable that people will want to build another next generation of gravitational wave detectors as we go forward. This graph, I think I'll skip it for time, and let me go on. So let's go on to some other kind of sources that we haven't seen yet. One example is burst signals. So the first one we saw were the so-called chirps. Went whoop, okay. The second class of signals, because we look at them as signals, is something that just gives some sort of burst of energy. And an example of that would be the collapse of a star, a supernova. It turns out that the so-called gamma ray burst isn't so different from that, but it isn't fundamentally a burst signal. So we have tried to develop the ability to look for signals that would happen like a supernova. We haven't had a supernova close enough to the Earth to detect during the time we've been looking, and we're not sensitive enough to look further out at this time, but we will be in the future. The idea is that we detect, if there's a supernova, a collapse of a star, we detect the gravitational wave signal first. It's the gravity pulling the star together. Then when it comes together, there's all the nuclear physics that happens when the star merges to a dense, really compact nuclear system. And one product of that is neutrinos that come out. And finally, the shock wave comes, and it's what creates the light, which is what people have detected. Those come out in time sequence. And what would you like to do in the end is have the whole picture of the collapse of a star to understand a supernova and what happens in a supernova. We've developed an alarm system where if we detect what looks like a burst signal, we send a message out for other astronomical devices or the neutrino detectors to look for signals. Of course, at this stage, we haven't seen anything yet. The supernova itself, understanding a supernova is a big problem and an issue. We have huge computer programs that are used in places like Lawrence Livermore Lab and other places to put in all the hydrodynamics and the physics of a collapse of a star. And yet these big programs, they can't make them reliably explode and so forth like a real star does. And unfortunately, we can't tell from those programs what the signal would look like for gravitational waves, because it comes from this so-called quadrupole moment, or a non-spherical part of the collapse. And in these large computer programs that are done today, by necessity, they make the simplification that it's symmetrical, spherically symmetrical. So in their calculations, there is no gravitational wave signal. So instead, to estimate the gravitational wave signal, we have more phenomenological analysis, not the huge computer programs that look at the neutrino signals that are known from supernova, the fact that the final product from a supernova goes typically at a few hundred kilometers a second, and models are made that then give us some idea what the signals will be like. My point is that we know first that there will be a signal for gravitational waves because the final object doesn't sit still, it moves along. So there's some sort of asymmetry in the system, but we don't know really how big the signal is or what the shape is of the signal. So it's something we have to be very clever about how we look. So we look in various ways in what we call unmodeled ways. This is a very active region of ideas, I'd say, inside a scientific collaboration. How do you look for something which you don't know what it's going to look like? So we want to do that for this, but we also have the idea that since gravitational waves come from totally different phenomena than electromagnetic waves, that we should look for signals that are gravitational that don't give electromagnetic, besides the black holes, that don't give electromagnetic or detected electromagnetic signals. So how do we look at all this data we have, not in the way we did with all these templates, but in some way that's completely unbiased and can find anything that's in the data itself? There's nothing biased in the way we take the data. So we do that by looking by various schemes. We have a whole active group that does this. The most successful scheme that we have uses a waveform, so some power excess that'll come because of the gravitational waves, that uses a mathematical technique that is called wavelets. And that basically is the heart of the best effort that we have. And it, unfortunately, is also biased because we can't really make a wavelet analysis without building in some prejudices about what a signal will look like. However, it was our most successful method to see anything because it's a little known fact that the first discovery of gravitational waves was not made with the template method that I mentioned at the beginning. It hadn't been even put into the device at that point, but was made first with this unmodeled wavelet analysis by two physicists from Florida. So basically, it's a useful method. We want to use it to model to find any sort of sources we haven't seen. So far, we haven't seen anything. It's an area where we need new ideas to look in an unbiased way. And probably, a promising method would be to use machine learning, a way that has nothing to do with us putting in biases, but looks at all our data and picks out, let's say, anomalies or things that maybe look different that we can look at. But that's, again, giving you a hint at kind of where we're against a wall and trying to figure out how to go in the future. So we try to look for unmodeled sources. So far, we haven't seen any, and that was supernova. The next kind of source of gravitational waves that we know about is from pulsars in our own galaxy. That's neutron stars that are spinning and making electromagnetic signals that we call pulsars. To remind you, a neutron star is the product of the collapse of a star that's something like smaller than, too small to be a black hole. The final neutron star typically weighs 1.4 times the mass of our sun. It's thought to have a solid crust of about a mile thick, and it's only about 12 miles across. So I showed you a black hole before. It's big compared to the neutron stars. And the inside is mostly some sort of a model, at least, as some sort of a liquid, many neutrons, and other particles. And what happens is a neutron star makes itself, when a star collapses, spins. It's made out of particles that have charges. Those charges make currents. Those currents make then electromagnetic signal that goes along the axis as it goes around. And there's magnetic fields as well. then that object is either pointing at you and you see it or it's not, a little bit like a lighthouse. So as a pulsar goes around, every time it comes around where you can see it, sending a signal toward the Earth, you see it. And the different pulsars are at frequencies that vary from tens of hertz up to thousands of hertz that appear once a star has collapsed and given a neutron star. These are studied in radio telescopes and in our own galaxy. So that's basically what's known. And as I said last time, I'll just say in words this time, what was found that gave an indirect evidence of gravitational radiation was neutron stars in our own galaxy like the ones I just showed, but two of them going around each other like the Earth and the Moon, and giving a signal that followed the calculations of general relativity and how they were merging toward each other, but much earlier in their lifespan than when we would detect them. So it's two neutron stars going around each other that a million years from now will make a kind of signal that I showed soon. And what they saw was that these neutron stars with very accurate measurements were slowly getting merging together or getting a shorter period going around each other. Anyway, the detection of periodic sources like these is not simple. If we know them, because they're out there, we look for them. And so those are okay. We look for them, but the ones that are out there and give a signal for radio telescopes turn out to be old. The fact that they give a signal that radio telescopes like is because they give a signal that's uniform. It's the same frequency all the time. It's a good clock, and they've been around a long time. But if that's true, they're typically very spherical, and so they don't give gravitational wave signals. What we expect is the ones that will give gravitational wave signals are the newborn or the young neutron stars after a star collapses. And those haven't been seen in radio telescopes, so we have to look at those. But if we look at the whole sky, the place where you look at a point in the sky is frequency modulated due to the motion of the Earth relative to the solar system, barycenter of the solar system. And so the intrinsic frequency changes with just its motion as it's going around. And the amplitude is modulated due to the detector's antenna pattern, depending on where it's looking. The combination of those two means if you want to scan the whole galaxy, it's a computing problem that's well beyond our capability on even the biggest computers. These are just some pictures of models of how graphically a neutron star might not be totally spherical. In pictures that, so we've looked at all the targeted known neutron stars, the main ones, not all, with our data. I show a little bit old data here, but it doesn't matter. And we've seen no evidence of gravitational waves. We look at it, we look at their frequency, and we look at the frequency that the gravitational wave would be emitted at, and we see no signal. And from that, from kind of the known, best known pulsars, we're able to say that the ellipticity of that sphere is tiny, 10 to the minus 8, and that there basically are no mountains on them more than, say, a millimeter or so. And that the amount of energy of these that is going out into gravitational waves is only a fraction of a percent at the most. We didn't see anything. In order to look at the younger ones, we have to do something else. We don't have the electromagnetic information to look at. So we try to scan the sky, and as I said, that's too big a computer problem for us, using all our computers. So one of our collaborators, named Bruce Allen, developed the idea that we would do something using background cycles on other people's computers. So we developed something called Einstein at Home. You can find it on your laptop when you go home. And we use background signals where somebody who joins isn't using their computer. And we scan the sky as much as we can to look for signals from gravitational waves from spinning neutron stars. We've seen signals from electromagnetic reactions that hadn't been seen before, but we haven't yet seen anything from neutron stars. If you want to help us, go to our website. Okay, lastly, and this is probably, in my mind, the most interesting of all, is cosmological signals. Can we see, with gravitational waves, signals that came from the first instance of the Big Bang? Looking at this plot here, you'll notice we're here, and we want to look back in time to the Big Bang. Everybody wants to know what really happened at the Big Bang. The problem is, everything we know comes from some form of photons. And photons only bring us back, it's actually a few 100,000 years after the Big Bang, because it was too dense here and the photons were absorbed. So when they look at what is called the microwave background signals, cosmic microwave background signals, we get some indication of the physics we know at the Big Bang, but it's looking at it after a long time, after 400,000 years. If we want to go to earlier times, there's only two possibilities. One is that we somehow detect neutrinos from the early universe. That would be 1 second after the Big Bang. The problem is neutrinos that have been around that long have become very, very thermal, what we call thermalized, very low energy. And they're almost impossible to detect because they're such low energy. So the best way to go back, we don't know how to do it yet, I'll show you the data and show you why, is gravitational waves that actually can go back to the very first instance of the Big Bang. Of course, the first instance of the Big Bang, we all want to know how it all started, what happened. But for example, we cannot, as of today, explain why and how, in the very first instance, or in the Big Bang itself, we created a universe that we live in that's made out of matter with no antimatter. If we go into our labs and we crash particles together, we make antimatter as prolifically as matter if we have enough energy. And so what was it in the very early universe that created matter over antimatter? And somehow we're left with all matter. This is a problem for physics. We have some ideas, but nobody can really explain it. So there's a lot about the early universe that to me is one of the most important problems we have. And the ultimate goal would be to do it with gravitational waves. That we can't do yet, at least very well. I'm going to skip this because of time. Because we're at very high frequency. So this is a picture of the strength that is measured, but don't pay a lot of attention to it, in many orders of magnitude of the gravitational wave signal. This is the cosmic microwave background. It's at incredibly effectively low frequency. We're way out here in what's called the audio band. And so we have to have some tail of this that comes out to us. We search for signals from the early universe. This is where we are. And we don't see anything, but we don't expect to unless the early universe has behavior that we don't really anticipate at present, although we'll get more and more sensitive. The right instruments in the future is to develop instruments that do gravitational waves that can work closer to the low frequencies, or do at least the equivalent of the cosmic microwave background experiment, and that's for the future. So that brings me to the future beyond us. So I kind of painted where we can go. In LIGO, we're in the audio band that's shown out here. This is frequency in many decades. And this is us now. And we will improve, as I said, as we improve things on the Earth. This is also the next step for gravitational waves, which is to do measurements of gravitational waves in space instead of on the Earth. On the Earth, we're limited to the audio band, 10 hertz to 10,000 hertz, where the Earth is quiet enough. By sending a gravitational wave satellite experiment up, you can probe lower frequencies. The experiment that's being done, or being put together, or being contemplated, is called LISA, Laser Interferometer Space Antenna. It's supported by the European Space Agency. It's scheduled for, unfortunately, what space experiments take, something like 2035. And it will fill this frequency band at lower frequencies, something like 10 to the minus 1 to 10 to the minus 4 hertz. If you took a signal like the first black holes that we saw, and this would have existed, they might have been able to see that signal before us a year or so and told us that it was coming, for example. So, because it was at low frequency before it got to higher frequencies. There's also a scheme to go to yet lower frequencies, and I'll show you that in a minute. So this is the space experiment, just to give you a quick overview. It's 3 satellites separated by 2.5 million kilometers, and sending signals back and forth between them. And if gravitational waves come along, they distort the time such that it takes a different amount of time to go from here to here than here to here, and they can see the warpage and measure the gravitational wave signal. It's in an orbit that goes around the Earth's orbit, the sun's orbit, as I said, like the Earth. And it measures frequencies that you can see here from about 10 to the minus 1 to 10 to the minus 4 hertz. The technologies have been developed to do this. This is the test of the technologies that they can make make both a detector where on the satellite the device are free to move, free masses, as I pointed out, and they could have the sensitivity that's needed to do the measurements in space, which is not the kind of sensitivities we have, not as accurate, but they don't have to be as accurate in space. So that's that experiment. This is the idea just shown here. There's 1 million kilometers between 2 satellites, and they have a test mass like we do in each satellite, and they detect the time it takes for the light to go back and forth. And be patient, that'll happen at about 2035. At yet lower frequencies, which is getting closer to the early universe signals, we can use signals that come from all these pulsars. It turns out the pulsars are very good clocks. So we've detected pulsars in our own galaxy, and they're well-known pulsars, and they tick at a certain frequency. If you look at what would happen if a very low frequency gravitational wave goes through, it distorts space and time, and differently, it'll affect the different measurements of different pulsars in a different way, and the combination of all those can give you the handle on, with very accurate clocks, on the arrival and the passing of a low frequency gravitational wave. So there are people that are doing that. They haven't detected any signals yet, but I can imagine that they will within the next decade, and at times we worried that they would detect gravitational waves before us, but they haven't yet. Lastly, you can hope to do polarization, do effects nearer what the people do that do the electromagnetic experiments, that is the cosmic microwave background signal, by looking for polarization imprints due to gravitational waves on their experiments themselves. There was an experiment that claimed to see that turned out to be not correct a few years ago, but people are working harder to do that, and I think it's likely that we'll be able to do that in the future. So the message is that we have lots of different ways in the future. I try to summarize that all together on this picture here. This is frequency. These are the different techniques. So we're here. We're at the highest frequencies, and we're on the Earth's surface. And we can do things like I show above, like look at pulsars or supernova or things that happen very energetically and very quickly. They give high frequencies. You can go in space and look at frequencies that are lower. And there's different sources, or even the same sources before they got so high frequency, like the black holes, maybe a year before we see them. And that'll be instrumented in this space antenna, maybe 2035. At lower frequency yet, I talked about the radio pulsar signals, and they can come from super massive black holes, for example, the big black holes you read about that are at the center of our own galaxy. And that'll bring us down to these frequencies. And eventually, we hope to get down to the frequencies that can detect the signals from the Big Bang itself. To detect them directly, we don't have a technique yet, but I think we can be optimistic that those can be developed in the future. So I'll end on a kind of presumptuous note that in 1607, Galileo put together the first telescope to do astronomy from lenses that were made at that time for glasses. People had developed the ability to make glasses, so he created a telescope. He wasn't the first one to create a telescope, but he was the first one to create a telescope to try to do astronomy. And The first experiment he did was to look at Jupiter. And when he looked at Jupiter, he discovered for the first time was something that hadn't been seen with the naked eye. And that is that Jupiter had 4 moons. It actually has more, but it had 4 moons. And that was the birth of astronomy. And now we've had 400 years of astronomy. And what we know about the universe is fantastic compared to Galileo's time, or what we could do with just our own eyes. So I think the first observation of gravitational waves, which we made, is a little like looking at the moons of Jupiter, and that if you give us another 400 years, that I think what we'll learn from gravitational waves may be as impressive as what's been learned from electromagnetic waves in normal astronomy. So thank you.
Thank you so much. So we have time for a few questions. If you'd like, there are microphones here. You walk up to the microphone.
This doesn't seem to, oh, there it is. Yes, if I could ask a very quick question. By the way, I'm a layman, I'm not a physicist. So I was reading about the first LIGO detection when they had a 36 solar mass black hole merging with a 29 solar mass black hole to form a 62 solar mass black hole, not 65. And they said that the 3 solar masses were released as energy, primarily gravitational waves. I was wondering if you could explain this to me. I don't understand how any mass can leave a black hole. Once the 2 black holes merge, their event horizons are together. I certainly understand why it would cause a ripple in space-time, but I don't see how the mass from the black hole could actually leave and become a source of gravitational energy. Thank you.
Yeah. Okay, so first, the question was totally coherent. So let me repeat the question and try to answer it a little bit. The two black holes that we detected were tens of solar masses, 10 times. One was 29, one was 32, after we drew these lines and fit to Einstein's equations. Meaning that at the point where they were early, I don't know what I did with my pointer. At the point back here, before they inspiraled together, that's where we really determine the masses from here. But when they merge together finally, during that whole process, they're emitting energy by slowing down. Don't forget, energy is made not just of static mass, but mass that's moving. So these are moving at relativistic velocities, and the total amount of energy is not, we say it's one mass and the other mass, but there's also all the velocity around. They end up merging and making something that's spinning at some. The total amount of energy in the universe is conserved, of course. But there's energy emitting in Einstein's theory to gravitational waves during the whole merger process as they're coming together because of the accelerations. It's not anything else than the fact that if you have accelerations, you emit gravitational radiation in Einstein's theory of relativity. And that was what his theory of general relativity was. It added accelerations to velocities. Whenever you have accelerations, which is what happens when you have a turn, then you emit energy. And all particles that we have, when we run a particle around a particle accelerator and it goes around a circle, it radiates away energy and we pump in RF energy to keep it going. In this case, some of the energy goes out, and you can calculate directly from Einstein's equations how much that is. And in this case, in the final 0.2 of a second is what the paper said, which is when we observed it. Something like 3 solar masses of energy were radiated away, which was consistent with the peak of this, which is how much energy was left in the system. The peak of this was consistent with, if you look at this, with 62, while this with 59, while this was the 62.
Yes, hello.
Hi.
When two black holes merge, is the gravitational wave, where is it originating from? Is it from the event horizon? Is it from inside? Where is it coming from?
No, it's coming. It's coming as a result of just think about any object accelerating. When it accelerates in Einstein's theory, it radiates just like if we have regular particles, an electron, and an electron is made in a circle, it'll radiate what we call synchrotron radiation. So we're aware of all kinds of radiation when the particles accelerate, including a black hole. In Einstein's equations, it emits gravitational radiation. That's the whole idea. And that's directly calculable, how much it radiates. It just radiates away some energy and slows it down.
I asked you this question, I think, a couple days ago. Can we use gravitational waves to look inside black holes? I mean, am I asking the wrong question?
Yeah. No, it's not necessarily the wrong question. I don't know how, but I would hope that by looking inside, can we understand more deeply the dynamics of black holes? And I don't know whether we can. We know how to do that for neutron stars. Let me say that. So let me work around the question a little bit. For neutron stars, we have this same kind of shape, and then they come together, and one thing that we're looking for is what are the nuclear effects after they come together, after the merger. And we know that then we look out here somewhere for all kinds of nuclear effects. Whether there are ways to do that, and there are even calculations of various theories of what happens to nuclear physics in very extreme conditions, very, very compact conditions. And we'll test that someday when we're sensitive enough at high frequency. We don't have the same theories developed, but I would hope they could be for black holes. And I mentioned at the very early part of my talk why. I think if we could use gravitational waves to study black holes, we're starting to be able to study, I really don't know what I'm talking about now, but I'm saying it anyway, that if we could use them to study it with the same kind of modeling and study black holes, then we have possibly a new laboratory to understand where quantum physics and general relativity have to come together. Ask me to go any deeper than that, and I can't. There are very few places in nature where we can kind of bring those two worlds together, because general relativity basically works at long distances and quantum physics at very short distances.
All right, are there any other questions? So there will be a reception at IPAM following this talk, so we can talk there. Thank you so much again.